Hello everyone, I'm Feng from Tsinghua University. Today I'm going to talk about our work, TriCache, a user-transparent block cache enabling high-performance out-of-core processing with in-memory programs. This is joint work with Ant Group. In recent years, new hardware gives NVMe SSD array a boost in performance. More PCIe lanes are available on CPUs, allowing for more PCIe-attached SSD. The new PCIe 4 and 5 standards enable higher bandwidth, and the U2 interface increases storage density compared to the former PCIe add-in cards. With the development of hardware, NVMe SSD array can achieve high aggregate performance. For example, a dual-socket 2U server can have 16 NVMe SSD attached for 50 TB capacity, 50 GB per second bandwidth, and 10 million IOPS. NVMe SSD array is cheap, light, and fast. However, it still suffers from block-wise I/O operations, high latency, and limited write endurance. Caching data in memory can help to mitigate these drawbacks. An efficient cache system can extend the memory capacity with NVMe SSD array. And also, in-memory programs can support out-of-core processing to handle data size larger than memory. Operating systems provide a page cache based on virtual memory and page faults. It's easy to use and does not require code rewrite for in-memory programs. Page cache has good in-memory performance on cache hits because it uses hardware TLB and MMU to take page table lookups, but it has poor out-of-core performance on cache misses. Page cache relies on hardware support of virtual memory, and the current CPUs cause the TLB shutdown problem and context switch overhead. In addition, the current Linux implementation uses global locking, and this makes the Linux page cache not scalable. Also, the Linux spends additional CPU cycles on its I/O stack due to the generic block layer and the device's driver. For OS page cache, to efficiently use NVMe SSD array, it needs non-trivial OS and CPU modifications. So what about user space solutions? In user space, some databases and data processing systems build their own block cache or called buffer manager. They can provide better out-of-core performance. Also, kernel bypass I/O stacks such as SPDK can efficiently operate NVMe SSD array. Meanwhile, block caches can easily support customizations, such as modifying block size and eviction policy. However, applying user space cache to in-memory programs bring high development costs. Users have to rewrite entire programs based on cache API calls. And they also need to be aware of blocks, manually check the block boundaries, and merge software cache lookups on the same blocks, which is costly. So we wonder if we could make the user space cache easy to use and not require code rewrites like OS page cache. This is the goal of TriCache, and if it succeeds, existing scalable in-memory programs can be extended to be efficient out-of-core programs. There are several challenges to be addressed. First, to avoid manual code rewriting, TriCache provides a virtual memory interface for in-memory programs with the help of compile time instrumentation. Second, the virtual memory interfaces lose the block information, so it forces the cache system to handle software address translation for each memory operation. For this challenge, TriCache adopts the idea of multi-level cache and proposes a two-level software address translation cache. Third, due to the synchronized nature of virtual memory interface, it's not easy to fully utilize NVMe SSD array. TriCache relies on good scalability to support the increasing SSD performance. We use message passing-based delegation and lock-free data structure to achieve scalability. This figure shows the high-level architecture of TriCache. In the following slides, we will introduce this figure and the design of TriCache step by step, and use an example to show how TriCache works. In compile time, the user application is compiled into a binary with TriCache runtime. The TriCache compiler plugin instruments memory accesses, such as load and store, and inserts TriCache runtime API calls. The compile time instrumentation of TriCache is based on LVMIR. TriCache address translation calls get raw pointer before each memory access, so it can redirect memory operations to TriCache runtime and its in-memory cache. After that, in-memory programs can use TriCache just like virtual memory. Meanwhile, CPU execute the memory instructions, so TriCache supports SIMD and atomic operations. In addition, TriCache modifies memory layout. Here is the current Linux memory layout. TriCache sets the highest space of address and puts its virtual memory space into non-canonical virtual memory. Therefore, checking the highest space in LVMIR can quickly identify user space or TriCache space memory. About libraries, recompiled libraries can be supported by TriCache, and TriCache uses library hooking to handle some common functions and use trap handler for libraries that have not been recompiled. For example, the memory allocations are hooked by TriCache to identify which memory is allocated on TriCache space memory. TriCache supports different policies by setting runtime parameters, including size threshold, memory usage limitation, or manual specifies. Here is an example on TriCache, computing the length of a string. In this code, there is only one memory access. After compile to LVMIR, TriCache instruments this access. Next, let's look into the design of TriCache runtime. For each user thread, TriCache builds thread local software address translation cache to handle its runtime calls, and we call it SATC for short. Under the SATC, there is a shared cache, which is a full-featured block cache. As in the previous slide, TriCache has multi-level cache. Multi-level caches can exploit locality, and with locality, the translated pointers can be reused, and the cost of multiple translations can be amortized. So multi-level cache can replace the human efforts on reusing pointers. The higher levels are smaller and faster, and store hotter data. There are 3 levels of cache in TriCache. Only the last level manages the data, and the upper levels only manage the address. The last level cache is named shared cache, and is shared by all user threads. On top of the shared cache, TriCache builds a thread local cache called private SATC. When it hits, the user thread can get the cache address from the private SATC. And only when the private SATC swap in or out some blocks, the user thread need to operate on the shared cache. So private SATC can reduce shared cache operations. On top of private cache, TriCache has a direct mapping cache named direct SATC, which supports fast lookup and maintenance. The direct SATC is also thread local and can be extended to be fiber local or coroutine local. It mainly targets consecutive operations on some blocks, such as sequential reads and writes. In TriCache, these 3 levels of cache use inclusive policy, which means all blocks in the higher level cache are also present in the lower level cache. The inclusive policy can avoid broadcasting, which is costly in software. TriCache uses reference counting on private SATC and shared cache to ensure inclusiveness. Now we are going back to the previous example. After instrumentation, the get raw pointer call checks the pointer on direct SATC. If hit, the translated memory address will be returned. Otherwise, direct SATC requests the address from private SATC, and so on. If still missed on shared cache, it will read the block from storage into memory, and responds to the user thread. Finally, the shared cache in TriCache. Multiple threads operate on the shared cache, and in shared cache, blocks and their backend storage are partitioned. Each cache partition is a server, and each thread is a client. They send requests and response to each other. Shared cache is built with message passing-based delegation. Each server of shared cache processes messages, cache management, and storage operations. The server is single-threaded, so it is easy to customize. And more server can give better performance, making shared cache scalable. In TriCache, servers only process metadata operations, while clients execute data operations by themselves. This keeps cache consistency and avoids redundant memory copies. When a user thread wants to access a memory location, it first computes the partition ID. The class then tries finding the blocks in server's block table and updating the reference count directly, which is cache hit fast pass. If failed, the client will send a remote operation to the server and immediately release CPU. After the server receives the request, it will maintain the cache, perform I/O operation if necessary, and respond the memory address to the client. After the client receives the address, it then does the memory operation. Here comes to the evaluation part. This is the testbed in our evaluation, and the testing storage has about 10 million random IOPS. The first part is end-to-end performance on 4 representative domains: graph processing, key value store, big data analytics, and graph database. They test the cache systems in different aspects, such as random and sequential access pattern, ability to exploit spatial and temporal localities, and the support of atomic memory access. For graph processing, we apply TriCache to an in-memory framework Ligra and extend it to out-of-core. The baseline are Ligra with swapping and FlashGraph, an efficient out-of-core framework designed for SSD. Here is the performance of WCC algorithms. In memory, Ligra on TriCache performs about 3 times slower than Ligra based on OS-based cache, but it is still about 4 times faster than FlashGraph. And on out-of-core processing, which is the target of TriCache. TriCache can outperform OS-based cache by orders of magnitude, and is comparable or even faster than specialized out-of-core systems. Other experiments on end-to-end performance can be found in the paper, and they also match these 2 conclusions. Next, we examine the design of multi-level cache by measuring the miss rate and hit cycles for TriCache when out of core. As you can see, SATC handle most of memory access. We further compare the hit cycles of ITCs to hardware latency in order to give an idea of how much time they take. 50 cycles are close to a NUMA local L3 cache hit, or L2 cache force sharing. 150 cycles are about half of a NUMA local memory access. 450 cycles are less than a cross-NUMA memory access. Therefore, TriCache with SATC is efficient enough to provide a virtual memory interface and also to deliver memory comparable performance. There is more evaluation in the paper. Micro benchmarks compare TriCache with Nmap and FastMap and show speed up and different access patterns. There are more detailed performance breakdown, including different storage backends, performance impacts of direct and private SATC, and the performance under different number of threads. To summarize, TriCache is a new user space cache mechanism that is user transparent and provides high out-of-core performance. Virtual memory interface avoids manual code rewriting. Multi-level cache design provides fast address translation, and good scalability enables high out-of-core performance. The source code of TriCache is available online. Thank you for listening, and I'm happy to take any questions.